Here, I've written probability of B given A and the probability of A given B. For this first one, I can multiply both sides by the probability of A, and this will give me probability of A and B equals probability of B given A times the probability of A. If I substitute this into this one, I will get probability of A given B equals the probability of B given A times the probability of A divided by the probability of B. And this result is known as Bayes' theorem. Bayes' theorem allows us to invert conditional probabilities. This is an example I wrote last spring, so the information is a little bit dated, but I think it's still useful. I found this information about a COVID test, and I think we can use it to examine how Bayes' theorem works. A test for a disease has these measures called sensitivity and specificity. Sensitivity refers to the ability to detect true positives. This test is 93.8% sensitive. So, given that a person has the disease, the test has a 93.8% probability of coming up positive. Probability of positive given disease equals 0.938. That would mean that if the person has the disease, they would test negative 6.2% of the time. Specificity refers to the ability to rule out true negatives. Given that a person doesn't have the disease, the test has a 95.6% chance of coming back negative. That means the probability of positive given no disease is 0.044. Let's assume that 1% of the population has the disease. I think it's probably higher than that now, but it was lower back when I wrote this. So if 1% of the population really has the disease, what is the probability of a false positive? What is the probability that someone who tests positive doesn't have the disease? In other words, what is the probability of no disease given a positive test result? Bayes' theorem makes it really easy to solve a problem like this. I've set it up based on the definition. We're given the probability of positive given no disease, it's 0.044. We're also given the probability of no disease, that's 1 minus the probability of disease, which is 0.01, so that's 0.99. We just need to find the denominator, the probability of a positive test. If a person tests positive, they either have the disease or they don't. So we can split the world into two disjoint possibilities, positive and disease or positive and no disease. And that equals this, where we're using the general addition rule. And here A and B are disjoint, so the intersection drops out. And so we have that the probability of testing positive is this. And we can find the probability of positive and disease by using the conditional probability definition, probability of plus given disease plus and disease divided by P disease And notice that we have this and this, and it allows us to solve for this. When we put this all together, we find that the probability of not having the disease, given that a person tested positive, is 82.28%. The reason this is so high is because of the assumption that only 1% of people have the disease. Because it's so rare, the vast majority of tests are performed on people who don't have it, and the false positives outweigh the true positives. Although, like I said, in reality, this assumption of 1% is probably too low now. We can generalize this. Let's say we partition A into n disjoint outcomes. We can split up B into n disjoint sets. Look at it this way. Here's A, and there are 4 outcomes in A. A1, A2, A3, and A4. And there's a 100% probability that one and only one of these outcomes occurs. Now, if we look at the outcome B, there are 4 possible things that can happen. B and A1, B and A2, B and A3, B and A4. Because these sets are disjoint, the probability of B can be written like this. Using this definition here, I can turn this into this. And that's where we get the version of Bayes' theorem you see in the book. The denominator comes from here, and the numerator comes from here. Here's another example of this. If you're told that an animal was selected from this house and that the animal was a cat, what's the probability that it came from bedroom A? If you randomly draw an animal from the house, there's a 4/9 probability that it comes from bedroom A, a 3/9 or 1/3 probability that it comes from bedroom B, and a 2/9 probability that it comes from bedroom C. And that's coming from how many animals are in each room. Looking at the probabilities of cat given bedroom, if you're told that the animal comes from bedroom A, there's a 2/4 or 1/2 probability that it's a cat. If it comes from bedroom B, there's a 1/3 probability that it's a cat, and there's 0 probability that you get a cat if the animal comes from bedroom C. We have all the probabilities we need to use Bayes' theorem. Plugging them in gives me 2/3. There's a 2/3 probability that the animal came from bedroom A, given that it's a cat. And you can deduce this from the fact that there are 3 cats and 2 of them come from bedroom A. But usually this isn't so obvious, and that's where Bayes' theorem can come in handy.